So what we're going to go through is I'm going to talk about moment. Just spend a little bit of time on moment, and we're going to talk about the differences between moment and work, and then we will go through some of the other just like basic calculation stuff. Okay. So what are we looking at? So we know that work is force times a distance, but that distance is parallel, right? So we know that, okay? So essentially work is in a straight line. So you lift something up, you carry it 6 feet, and you put it down. Or you move it, in a straight line of some kind, right? I'm gonna give you another one, it's called moment. It's also force times distance, but instead of the distance being parallel, it's actually perpendicular, right? And the best way that I can give this as an example is that when you have a door, like a typical door, you guys know that when you try to open the door very close to the hinge, it's pretty difficult, right? Right? And the further you move your hand away from that hinge, the easier it is to open that door. Yeah? Anybody know why? Why do we think it is that way? No idea. Okay? So how many people know what I'm talking about, but it's hard to explain? Okay. So let me explain it for you. So basically what you're looking at is the further you get away from that hinge, one of these two things is getting bigger. So either force is getting bigger or your distance is getting bigger the further you get away from that hinge. Which is getting bigger? Right, so the distance is getting bigger, right? So essentially what we're doing is when you make that distance larger, even if you keep the force the same, when you make that distance larger, what happens to the moment? It also gets bigger, right? Because your distance is getting bigger, your distance, a bigger distance times the same force, you're gonna get a bigger moment. So essentially the force, and I use that term lightly, right? That force that you're creating around that hinge is not actually called a force, it's called a moment, right? And when you open up that door, you're creating a moment. So think of a moment as like a rotational force, okay? So when you turn a steering wheel, you're applying force, but you're applying force in a rotational direction. So we call that rotational direction, we call that a moment, okay? So that's one of the key things here. So if we look from the top of a door, so I've drawn this picture a few times before. So here's the hinge, there's the door opens or closes, either way, it doesn't matter, all right? If you put your hand very close to the hinge and you try to open it, you look like that. So you have a pretty small distance. The further you get away from that hinge, and you do the same thing, if we could continuously go around, look how much bigger our circle is. So our distance is significantly larger, right? So that distance is what's helping us, right? Well, here's the nice thing. This circumference of this little circle and the circumference of the big one are kind of in relation to like this distance from here to here and here to here. So they're like a relational value, okay? So all you need to know is moment equals force times distance, and that distance has to be perpendicular, sorry, right? So how does that work for us in our math, right? So let's take a look at a first class lever. We use a first class lever because it's the easiest we can look at. And let's just say we have FE is 10 pounds. We have FR, which is 30 pounds. So we're going to pick up a 30-pound object only using 10 pounds of effort, right? So right off the bat, and we've done this one before, if we wanted to find mechanical advantage, if I wanted you to find AMA, what would you do? Well, you would say FE, I have 10 pounds, FR, I have 30 pounds, I need to find AMA, so you do FR over FE, America's free, right? So you would have AMA equals 30 pounds over 10 pounds. Those pounds would cancel, and you would be left with AMA equals, somebody said it, 3. So it's 3 times as easy. You're 3 times as strong. You can lift up something that's 3 times heavier than what you're applying, right? Okay. So that's a pretty easy way of doing it. That's just like a basic mechanical advantage solving, right? So how does it work when we want to go a little bit further? So what I'm going to do is I'm going to do this, get rid of this. That was kind of just review. And we have to talk about one more thing. It's called static equilibrium. Now, I don't know if you got to that point in your PowerPoint yet. Did you guys? No? Okay. So static equilibrium. Anyone have any idea what equilibrium means? You guys have heard that word before, probably in science class or something like that, right? What is equilibrium? Somebody said equal, right? So, care to explain a little bit more?
Maybe when something is perfectly balanced, or
Okay.
Yeah.
So perfectly balanced. That's a pretty good way of saying. I'm glad you didn't say just everything is equal, because the problem with being equal is, like right now, 10 and 30 is not equal. Okay. So what we need to do is essentially put this thing in a static equilibrium. What that means is we need to make sure that fulcrum is exactly where it needs to be, so that when you put 10 pounds on it and 30 pounds on it and you let go, what happens? Yeah, it stays right where it's at, right? So technically, static equilibrium means it's in complete balance, it's not moving, or it's at a constant velocity. Essentially, nothing is changing, okay?
If you move the fulcrum over like closer to the 30-pound side to like make it like try to make it equal, would you have to turn it into like a distance formula between like the space between two of them?
Exactly. That's exactly where we're going. Right? So my example that I can do in front of you is I take my meter stick, my yardstick, or whatever you want to call it. This might be a little too heavy. Let's see. So right now this is 100. It's a meter sticker. So it's 100 centimeters, right? So my finger is right now at 50. Why does it need to be at 50? Because there's even weight everywhere, right? It's continuous. What happens if I take this thing and I put it on your right, my left, right? What's going to happen? If I just let go, it's going to tip over. So what do I need to do to make sure this thing doesn't tip over?
Move your hand closer to it.
Yeah, I'm going to move my finger closer to that weight, right? Right? So right now this thing wants to go this way. As I let go, it wants to go up. So I'm too far. So I got to come over here a little bit. Now I'm too far that way. Slowly find that spot. Like that. Right? Now that was just trial and error, right? That was just trial and error. Okay? We can actually calculate that. We can actually figure out exactly where my finger needs to be without even playing with it. I can literally just calculate it, stick my finger right where it needs to be, and it will stay there. Okay? So essentially, we want to know how to calculate those numbers, how to figure that out. Okay? So, how do we do that? Well, before we get to that, let's give you a formula that you need. Okay? Essentially, what you guys are telling me, when we're trying to put this thing into balance, into static equilibrium, you're trying to tell me that the force and distance over here needs to be equal and opposite to the force and distance over here. So force and distance, so the moment over here on the left, the moment over on this side needs to be the moment over on this side. So what you're saying is the moment of the effort needs to be equal and opposite, which, because it's on the other side, it will be the moment of the resistance. Okay? So let's break down that formula, because that's very, I guess you would call it like truncated. It's not broken up. Yeah, so let's break it up. How do we find moment? We just talked about, how do we find moment?
Force times distance perpendicular.
All right, so force times distance. Let's do ourselves a favor, be a little bit more organized. So instead of being force and distance, because if we do force and distance on the right-hand side, then we're gonna have F and F. We're gonna have a lot of the same variables. So let's put an E on these things. So FE and DE, those are very familiar to you, right? We've been using them since. Put an equal sign there. Moment on the right-hand side is also force and distance. And what subscript are we going to put over here? Yeah, resistance. So essentially the F and the D on one side, so the F and the D from the effort, and the F and the D from the resistance. Those two things are going to work in combination to each other, and they're going to oppose the opposite side. We're going to set this thing into complete balance. Okay? Now, all of those variables, are they pretty, you guys have seen them before, right? So that's nothing new. So this formula, you're definitely going to want to write down this formula. We call this formula, a lot of times you'll see it referred to as the static equilibrium formula. Static equilibrium formula. What that static equilibrium does is it sets this thing, this first class lever in this case, sets this thing into static equilibrium. This is the formula you are probably going to use 95% of the time in this class for simple machines. This is like your go-to formula. Okay? All right? I can tell you, you're going to get a formula packet today. I can tell you this formula is not on the formula packet. Okay? It's one of the few that are not on there. Okay? But here's also the nice part about it. You can also, if you ever forget it, which you honestly probably won't because we're going to use it so much, you can also find it by doing this. If we do IMA equals AMA, which in the real world is impossible, we haven't come to that yet, but we'll get there. How do you find IMA? IMA here, so DE over DR. And America is free, so FR over FE. When we cross multiply those things, what do you get? You get FR times DR. So you get FR and DR multiplied together equals FE times DE. So you get that formula. Okay? So that's one way you can find it. But that formula right there, that FE times DE equals FR times DR, it's going to be the formula. It's going to be your go-to formula. Okay? Between that formula, IMA and AMA, those three, probably 99% of what you're going to do for this class for simple machines. Okay? So how does it work? Well, let's jump back to our first class lever here. Let's just say I put a distance on this thing. Give me a distance.
2 inches.
2 inches. All right. Perfect. So I want to know how far the other distance has to be. I want to know how far the other distance has to be. So the first question that comes up is, Mr. Burson, you gave us two distances, but you didn't tell us, because you didn't write it down for us, you didn't tell us which one is DE and which one is DR. So can you tell us? My answer is going to be, no, I can't tell you, because I've already told you. It's just not written there. Which one is DE? Which one is DR? And how do you know? How do you know which one? Which one is which? Come on.
2 inches would be DE.
Right, so 2 inches is the DE. Now, why you say 2 inches is the DE? What does DE stand for? What does DE stand for?
Yeah, but that's, the distance is caused by the effort of the force effort. So since you're using force effort right there, then DE is how much distance is caused by you using that amount of force.
Right, so it's the distance related to the effort. In another way of saying it, it is the distance from the effort force to the fulcrum. It's how far the effort force is from the fulcrum. Okay, so is that distance definitely how far the effort is from the fulcrum? Yeah. How far is the resistance from the fulcrum? Well, we don't know, but for us right now it's X, right? So that's our dr. So the DE and the dr are relational to their forces. So FE and DE are relational to each other. FR and DR are relational to each other.
Well, I thought I got it.
Okay, so she's a pro, she's on it. All right, let's try it. So, scroll down here and get rid of this. So what do we know? Well, we know that FE is 10 pounds. We know that FR, 30 pounds. We know that DE is 2 inches. We don't know DR. We need to find DR. So do we have a formula? So we just did given and unknowns. Do we have a formula that has DE, DR, FR, and FE in it? Yeah, that formula. What's that formula called? Static equilibrium. So FE times DE equals FR times DR. So we have 10 pounds times the distance of the effort, which is 2 inches, FR, which is 30 pounds, times the DR, which is, I'm going to leave it DR. I don't like to use X, even though I drew it in the picture. I don't like to use the word X, the letter X. I like to just keep the variable, all right? So, what do we do first? Now, some other classes got a little tripped up here, because they were like, well, we can't do anything, Mr. Bernstein, because it's 10 pounds and 2 inches. Well, they're not like units, so we can't combine them. The rule of thumb is when you're adding things, you can't combine unlike units. But when you're multiplying things and dividing things, you can combine them, or like decombine them, I guess you would say. Right? So we can simplify the left-hand side. So what's 10 pounds times 2 inches? Yeah, we get 20, and then what's the unit?
Mystery.
It's not mystery. Pounds, inches. That's what it looks like. So 20 pound inches. So you just keep those units, you multiply them together. You can't do anything to the right-hand side because it's simplified as much as you can. Now, what do? We have to get DR by itself. So right now it's being multiplied, so we're going to divide, right? So we're going to do 30 pounds, divide 30 pounds. That's going to cancel those things there. 30 pounds here, which is good because now we have pounds over pounds. So those cancel. We're left with inches. That's important because what type? Right, it's a distance, right? So we need to have a distance unit. So 20 divided by 30?
Well, 2/3 inches.
2/3, which is what decimal? So 0.66, repeating, yeah. Essentially inches DR. So if you were going to try and create that actual example, you would need a 10 pound force, a 30 pound force, it'd be 2 inches from the fulcrum, and then 0.667 inches from the fulcrum on the other side. Okay? Now, some questions come up. Where do you round? What type of, do we keep it in a fraction kind of thing? I'll tell you this. Engineers are not fraction people. Okay? Engineers are not fraction people. Just don't like them, okay? Even though they're exact, yeah. But at the end of the day, when we're trying to just finalize, we're gonna put it into a decimal, okay? All right, so 0.667 inches, okay? How we feeling? Good? Okay?
So is that the moment?
So that is not the moment, that is your distance. So that's how far this x needs to be. So you would essentially get rid of the x, you would put 0.667 here, and then this thing is in static equilibrium. So your question, to answer your question, what is the moment, right? What is the moment? Well, what is 10 times 2? 20. What is 30 times 0.667? What's 30 times 0.667? 20, right? So the moment over here, which is 20 pound-inches, is equal, going this way, and opposite to the one that's going over here. That's why it's in balance. That's why it's in static equilibrium. That's the key word.
What's this like moment and like why is it called moment?
Why is it called moment? Like in terms of like why don't they just call it rotation or something like that? Is that what you're asking? I honestly don't have a good answer for you. I would say probably because I don't know. I can't even come up with something. Questions? So I'm not going to do another one, but I'm going to put another drawing on the board just to make sure we can identify spots. So what if I did this? Let's go kind of like a wheelbarrow. So this is effort. This is resistance. Can somebody come up and draw for me where like DE or DR is? Just DE or DR.
Isn't this, DE right here,
Exactly. So that's DE.
and then I'll just do it right here.
Perfect. That's DR. So, what do you notice? Those distances go from what to what? Yeah, they go from themselves. I like how you said that. From themselves to the fulcrum. From the E to the fulcrum. From the R to the fulcrum. They do not go to each other. They go to the fulcrum. Okay? All right? Question.
So DE is just like here.
In this case, DE is the whole thing. The whole entire bar. Yep. Okay?